This is introductory to the three-dimensional coordinate system. So this is 12.1, introduction to the three-dimensional coordinate system, multivariable calculus. We've got the x-axis, the y-axis, and the z-axis. So this is just the introduction to the three-dimensional coordinate system. All right. So we could start by just talking about, well, how do you draw like the x and the y and the z-axis? Because this is a two-dimensional plane, or you have two-dimensional pieces of paper. So a lot of times you can think of it like that, where this is the what? The y-axis, this is the x-axis. You could stick the z like this. And now I'm going to change these. And watch what I'll do. What I'll do is now, I can just say, okay, I'll let this be the z-axis. This axis here will be my y-axis, and it'll be the x-axis right there. But that's one way you can look at these. And this would be the positive x, right? And this would be the negative x. Negative x. Down this way. Positive y, this is the what? Negative y. Positive z and the negative z. Sometimes when I draw this, you'll notice I might just do this. Just kind of swing this up like that. Just to show the positive axes. Y-axis, x-axis, z-axis. But some of you might want to show where it went negative, right, and extend them. Sometimes I just do that. But it's up to you in terms of what you're drawing on your piece of paper, what you prefer. So you know if we're doing something. You know, we used to call them quadrants, right? Now we have octants. There's 8 octants. We're usually in octant 1 with a lot of these problems. That's where the x and the y and the z's are all positive. All right? In octant 1. But when you can draw it like this, you can do it like this, either way when we make some sketches and stuff. But when it comes to plotting a point, you know, if we had to plot the point what? Let's just say we had to plot 0, 2, 0. Well, this is the x, that's the y, and that's the z, right? Go 0 for x, go over 2 notches for y, and then go 0 for z, it'd be right on the what? The y-axis, true? It does look weird when you do like a 1, 2, 3, because you do what? 1, cut over 2, up 3, and it looks weird because it looks like you just have a dot in a piece of paper, true? But sometimes we understand that because it is three-dimensional space as we write on these two-dimensional piece of paper, two-dimensional green board here. Cool. So I'll do this a lot, but I also do that as well because sometimes we're talking about what if it went like -1 for x, but then 0, 0, then I'm talking about what, right there? Okay, to -1, 0, 0. Okay. Well, do you remember the distance formula between 2 points in two-dimensional space? The distance formula in three-dimensional space is very similar. I'll just put d for distance. It has a square root. We did this in two-dimensional space. That was based off the Pythagorean theorem. Did you know that? Mm-hmm. That's why everyone, if you see in Canvas, I made like an intro to the. If you want to watch it, I made a little PowerPoint. Talks about a lot of these things are based off the Pythagorean theorem, even the equation of a sphere, which we'll show in a second. But if it's three-dimensional space, what do I have to add here?
Z.
Yeah, you got it. That's all we had. Now you add z2 minus z1 squared. That's the distance between any 2 points in three-dimensional space. So we're like, okay, let's find the difference between 1, 2, 3, and the point what? 4, 5, 7. What's the distance between those 2 points in three-dimensional space? To the 4 minus 1 squared, the 5 minus 2 squared, and the 7 minus 3 squared, right? And you'll find the distance between those points. What is 4 minus 1?
3.
5 minus 2. And 7 minus 3. And we're going to now find the distance between these points. Okay, what is that?
Square
9 9 and
16,
16. 18 plus 16 is,
32.
I guess, can I leave the answer like that? I thankfully have you to catch my errors when I screw up. And you will catch it if I mess up something on that. Look okay? So we know how to find distance between 2 points. Well, let's talk about that sphere equation. This came from Pythagorean theorem. It was derived from the Pythagorean theorem. So is the equation of a sphere. Well, we can first think circle, and then we'll make a sphere. Now, when this is the equation of a circle with a radius of 3, you probably recall this. I'll get other ways you can see this. Equation of a circle. Radius 3 centered at the origin would be x squared plus y squared equals 9. That's in two-dimensional space, right? You'll notice this actually came from Pythagorean theorem. The equation of a circle was derived from it. We can get the equation of a sphere. It's also derived from the Pythagorean theorem. You know what the equation of a sphere would be? It kind of looks like this. See, this thing, everyone, what if you shifted the circle here? You know what you had to do? You had to go x minus a squared plus y minus b squared equals r squared. Did you know that? The AB would be the what? The center of the circle? That's two-dimensional space. So what's the equation of a sphere? I'm talking about a ball. What's the equation? It's going to look just like, it'll be x minus a squared plus y minus b squared. Now what?
Z minus
There you go. You're extending this to three-dimensional space. Outstanding. And if you want to prove it, it'll take you like 2 steps if you want to prove that. And I'm going to put r there. There's the radius of the sphere, r squared. You'll see those on the point sheet. So let's talk about that one before we leave 12.1, the introduction to three-dimensional space. Let's talk about finding, like, let's do distance again. Well, let's not also work with a problem with the sphere. We can talk about it. Probably not to sketch it. The sketching becomes big time in section 12.6. You notice we won't get there today. I'll pass out a document. We'll make sure we're making some decent sketches of the types of surfaces we see in this class. This is a cool course. We see some neat surfaces. We see, of course, we got the spheres, but you have, ellipsoids. You're gonna have paraboloids. All right, you're going to have hyperboloids. Hyperboloids are 1 sheet and 2 sheets, some really neat things. All right, just don't turn into a geek like me and start trimming all your bushes in these shapes. It just means I've been teaching Calc 3 too long. That's all it means. All right, so here's my first one. I actually have one like this, taking it from like the practice set. What's the distance? You'll see a problem like this in 12.1. From all right, how about -1, 3, 4 to the z-axis? What is the distance from that point to the z-axis? All right, we don't even have to draw this. If you want to make a drawing, you can. As on the z-axis, if the point's going to be on the z-axis, then the x and y values will be what?
0.
0. Does everyone agree? If I'm talking about the distance from this point to a point on the z-axis, then on the z-axis, x and y take on the value 0. You can always think of that's what a z-intercept is. The x and y's are 0. So I'm basically trying to say, how do I find the distance from this point to, like, what's the other point that we're looking for that's on the z-axis? We'll do a straight line distance. Well, we're saying if it's to the z-axis, x and y both got to be what?
0.
Now, if you're curious, what should I use here? I want you to use the same number, because that will give you the shortest distance there. Let me say it again, so you're not confused. I'm going to use that same number I see there here, because that means I would take the shortest distance to that z-axis. And we'll take this, and we're just going to plug in what?
Just transform
Okay, right in the formula. Let's just see what we get. All right. And you see I have a problem like this on the practice set. What's negative 1 minus 0? What's 3 minus 0? And what's 4 minus 4? Well, 4 minus 4 became the what?
0.
That's
9.
3 squared, and a negative 1 squared is positive what? So what's the distance? Y'all get root 10? Great job. Hey, you don't have to work out this problem. I said to the z-axis, if I said to the x, y plane, okay, and when in the x, y plane, if I didn't write that, the x, y plane, z takes on the value of what? 0. And so what you would do there is, it'd be a little different. What you do is, xy plane z equals 0. So you have to make this a 1. I just wanted to change the problem a little bit. I know we just did z-axis. We go, well, what about the xy plane? Well, the xy plane, that's where z takes on the value of 0. So this would have to be a 1. 0. But you know what you'd use here? You'd use those same numbers. That's what you do. You can probably do that math in your head. What's the square root of that minus that squared?
0.
What's that minus that squared?
0.
What's that minus that squared?
4 square.
Distance is 4. And they're like, and that might make sense to you. Go, yeah, you just have a distance of 4. You just go straight to that plane and be 4. Cool. Hey, on that note, what is equal to 0 in the YZ plane?
So YZ plane.
In the YZ plane, what's taking on the value of 0? X. Very good. And one more plane, the XZ plane. What takes on 0 there?
Y0.
There you go. Does that help? Cool. So we just did intercepts, like X intercept. Oh, Y and Z are 0. But if we said YZ plane, we're saying, well then only X will be 0 in terms of all the points on that plane. All the points on that plane. And when you want to see those planes, I know, it looks kind of funny on our paper, but we're like, it looks something like this. I put the Y-axis here, the positive X-axis there, that's the positive Y, and that's the positive Z, right? And if you ever want to, and some students like to do it, they like to get the negative axes involved too. They start extending these, extend that down. I just don't want to give you too many lines to draw on your paper so it looks weird. Alright, so let's talk about that sphere. Let's do a part A, part B. What is the equation of a sphere? Let's see. I'm going to give you the center. With the center, what do they got? Yeah, I'll do 2, -3 and 4. And the radius is 5. So I think you'll find letter A pretty easy. This will be letter A, and then we'll go to letter B. What's the equation of a sphere? Center 2, -3, 4, and radius 5.
You want us to do it?
Yeah, what do you get?
X minus 2 square, y plus 3 square,
Good job.
plus z minus 4 square equals to 25.
And you squared the radius, very good. Is that what I go that? I do want to point out in our course, most spheres are centered at the origin. This one isn't. I know, we're seeing it in 12.1. Most of the spheres we're going to deal with, especially in terms of design, you just center it right at the origin. But here's part B. It's the intersection. Alright. I just want to choose a different plane than the one I had in my practice set. They had XZ plane here. I think I'll do with the XY plane. What is the intersection of the sphere with the XY plane? What I'd like you to do is, first, can we come up with the equation of what we're talking about? And then can you all help me just describe what this would be, what it would look like, and we'll do that. So here's this big sphere, right? Gigantic sphere, we know the radius was 5, that's the center. We gotta find the intersection of that sphere with the XY plane. What do we know to do about the XY plane? Something 0. What is
Z.
Z? And we're gonna take Z equal to 0, we're gonna substitute 0 into that Z right there. Do you all agree? That'll be our equation, but we'll fancy it up. We'll make it look good. When I heard it, you're like, just take this x minus 2 squared plus y plus 3 squared plus, and here we go, 0 minus 4 squared equals 25. Great. We knew what to do. Z equals 0 in the xy plane. But that number is now what?
16.
So let's take it, we're going to subtract it. That's 16. What's 25 minus 16?
9.
So I'm going to take it away, subtract it from the other side, and I think this looks better. I'll leave my answer like this, right? That's my equation. What is that? I was wondering if you could describe it. Yes! Man, they said it's a circle, because when I think of it, it's like, if it helps, think you have an orange and you just took a slice out of the orange. You're like, oh, I just took out a circle. If you want to say disc, you could say disc too if you're thinking like everything inside of it. But I like the word just describing that equation right there. It's a circle equation. It's a circle.